Okay, thank you very much and welcome everybody. So I'm Ferenc Hegedűs from the Budapest University of Technology and Economics from the Department of Hydrodynamic System. And now I would like to talk about my latest development of a program code which is capable to solve large number of independent ODE systems, of course using GPUs. First of all, why is it important to deal with ordinary differential equation systems? Actually, the answer is very simple because many physical, biological, economical and social processes can be described by ordinary differential equations. Even if we have partial differential equations, usually we can decompose them into a large system of ODEs. The next question is that if we have initial value problems of ODEs, how can we apply massively parallel computations in these cases? Basically, there are two approaches. First, let's take a really huge ODE system and try to assign threads to each individual equations, and that's how we can harness massively parallel computing. Such kind of problem may arise from the discretization of partial differential equations or by global coupling or diffusional coupling of many identical ordinary differential equations. The other approaches can be if we have smaller system, but we take many of them, which is actually identical but independent. But the only difference is the parameter set or the applied initial conditions. In this case, we can perform parameter studies, for instance, analyzing bifurcation of nonlinear systems, or we can examine the Bayesian of attraction of nonlinear system of some attractors. During my presentation, I would like to focus on the second approach, and actually I have many experience in nonlinear dynamics and bifurcation analysis, and I have approximately 2 years experience in GPU computing. So let me demonstrate that how parameter studies work with one of my latest results. Here we can see a parametric study of an acoustic bubble. The underlying physics and the equation is not important right now. The point is that we have two parameters, vertical axis and horizontal axis, and we can scan with very fine resolution the topological behavior of the found periodic orbits. Here, the color code is the period of the found attractors up to period 6. And the point is that just merely isolating the very fine topology of the periodic orbits, we could find a new technique to control multistability, which is a non-feedback technique, and with which we can directly target certain attractors. I said we because this project is carried out within the framework of an international cooperation with the Third Institute of Physics in Göttingen and with the Max Planck Institute also in Göttingen. The main message from this picture is with very fine resolution of parameter scan, we can open a new topic in a totally different scientific fields, because we just started from acoustic bubbles and we end up in control of multistability. So it can be very, very useful to make such kind of brute force techniques. Okay, so I had experience with GPU programming, but the problem was that my codes are usually specialized on certain systems. And if I wanted to examine other kind of system, usually I had to rewrite some parts of my code, and it was really uncomfortable. So actually I decided to develop a general purpose modular parametric ODE solver. The main aim was to be able to change the system very easily and actually set up the whole problem as easily as possible and make it similar to MATLAB. Okay, the main concept is not to store all the points during the integration of the trajectory. It has two reasons. One is I want to keep my program fast, And secondly, if I want to scan millions of ordinary differential equations, I can easily blow up the required storage capacity of hard drives. In my previous picture, I had 250 million initial value problems in my previous pictures. Okay, but usually if we find certain attractors, we try to extract some features of attractors. So I actually implemented a flexible event handling algorithm, and for storing special features of attractors, I use a technique to store them very efficiently. I just call them accessories. I will explain it a little bit more detail later that how these two technique works. Okay, so basically we would like to scan millions of ordinary differential equations. They have the form like that one, x dot equal some nonlinear function in general. The arguments are x, t, and p. X is the state variable organized in a vector. T is the time coordinate, and p is a set of parameters. So first of all, we have to set up a so-called problem pool, and we have to specify all the properties of all the individual independent equations. We should keep in mind that all the ODE system has its own time coordinate, which is denoted by t0 and t1. So first of all, we have to specify all the initial and the final times, and we have to specify also the initial conditions of each of all the ODE system, and similarly we have to specify all the parameters. I don't want to get very involved in details that how should we build up this problem pool. We should keep in mind that this data should be organized in such a way that later on when we run them in a GPU, we must access them in a coalesced manner from the global memory. And the basic idea is to assign one thread to one ODE system and solve them in parallel. But of course, if we have millions of ordinary differential equations, we don't want to put all the millions of equations in one GPU at a time. So maybe we would like to separate for smaller tasks and maybe to different GPUs. For this purpose, the code has a certain class which can be initialized with few parameters, for instance, the number of the threads. And we can create an object, I just called it here scan system with this configuration. And with special member function, we can copy some portion of the data from the problem pool into the internal storage of the object. And we can actually perform the integration between the time domain, only the problems which is copied into the object. Okay, some technical data. If the number of the problem size is NP, which is in the order of the million, then usually the number of the problems in the object is approximately in the order of tens of thousands. Okay, and after that, how can we perform the simulation? First of all, we have to configure a solver. We have to specify how many threads we would like to use in a certain block. We have to specify the initial time step, and we have to specify the numerical algorithm we would like to solve it. And after that, we have to call a member function called solve with this configuration, and after that, we will have the results. Right now we can choose two different algorithms, an adaptive Runge-Kutta method and a fixed order Runge-Kutta method. Later on maybe we can extend it with other algorithms. Okay, so but how it works in details, this parametric solver? Let me show you with some examples. The first example is the classical Duffing oscillator. It's a second order differential equation written in a first order system. We have two parameters. P1 is the damping parameter and P2 is the excitation amplitude of the external forcing. And we should keep in mind that the state space is actually periodic in time. The period is 2 pi. So for all the individual ODE system, we can just set the initial time to 0 and the final time to 2 pi. And with a simple for cycle, we can just call one after another the solver member function. And after each call, we can just save some properties of the system. So this is a periodically forcing oscillator, so we can observe that if we call this solver one after another, we just actually sample the trajectory with 2 pi, which is the period of the excitation, so it's actually the Poincare section of the system. How can we define the right-hand side of the function? For this purpose, we have a user-defined function called ODE function. It's very simple. For convenience, I define these variables in advance. x1, x2, p1, p2 is the state variables and the parameters. What we should keep in mind only is the indexings here, 0 and 1, 0 and 1. And after that, we can specify the right-hand side in a very human-readable form. Okay, we can set up ODE options with another user-defined functions called ODE properties. We can specify the relative tolerances, absolute tolerances for each component of the system, and we can specify some properties of the time marching, like the maximum time step, minimum time step, and in case of the adaptive algorithm, how the time step should grow or shrink. If we do not specify any other options, then we can calculate the Poincare section. It looks like that. In the vertical axis, we have the first component of the Poincare section, and in the horizontal axis, we have the P1 parameter. The P2 parameter was constant. Okay, it's not the point to explain that why does it look like this. It's just an example. Another example is a little bit more complicated. This equation describes a radial pulsation of a single spherical bubble. The bubble radius is r, which is a function of time. We can see that this equation is much more complicated, but it's still a second-order differential equation, but it has a much complex form and it contains much more number of parameters. In the following, I will denote x1 to r, which is the bubble radius, and x2 is the bubble wall velocity. Actually, this system is a dual frequency-driven system with pressure amplitudes and frequencies, and in general we have a phase shift also. And I choose the control parameter to the pressure amplitudes and the frequencies. For simplicity, I choose the phase shift to 0. But still we have a 4-dimensional parameter space. The resolution for each parameter was 100. So with a quick calculation, we can imagine that it means altogether 100 million initial value problems. Okay, but the main aim is to calculate the so-called collapse strengths of a bubble. A bubble can collapse so violent that inside the bubble the temperature can elevate to thousands of kelvins and chemical reaction can take place and so on. And a good measure for the collapse strength is, for instance, the radius of a local maximum divided by the radius of a local minimum. And if we divide the two values, it's actually a compression ratio. So our simulation works like that. We start the integration from a local maximum. We integrate the system forward in time. We try to locate the next minimum and integrating further and stop at the next local maximum. And in this case, we can repeat the simulation as many times as we want and register the collapse strengths. Now we can use, or we have to use the so-called accessories. We have to store 4 variables: the local maximum, the initial local maximum, the time instant, the local minimum, and this time instant, because sometimes the Alpes time is also matters during the calculation of the collapse strength. So it means 4 variables. So we need to set up 4 so-called accessories. First of all, we have to initialize them. We can do that with a special user-defined functions called initialization. During an integration period, it is called only once at the beginning of the integration, and we can set up the accessories, which is simply the index 0 is the first maximum, is the bubble radius is x1. We need to specify the corresponding time to the second accessories, and the third and the fourth accessories is saved for the next local minimum and this corresponding time instant, but we have to initialize them also during the computation. And after that, in another user-defined function, I just call it ordinary accessories, we have to keep track the minimum value of the trajectory. At every successful time step, this function is called, and we just simply have a check that whether the new accepted time step is smaller than the already stored one, and if it is smaller, then we can just replace it. And of course, we have to replace all the corresponding time instant. Okay, but in this way, we can identify the minimum point, but we have to stop the simulation at the next local maximum. So we have to specify even functions. Also, it works very similar as in case in MATLAB. This means that the x2 must be 0. In that case, we can stop the simulation. We have to specify the even properties. It's very similar as in case of MATLAB. -1 means stop at local maximum. Detect at local maximum, we can specify tolerances. And even stop condition means that after how many detected events we should stop the simulation. Another important thing is finalization, because we have dual frequency driven systems. So in general, we can quasi-periodic forcing. So all the time we have to keep track where we are in time. So at the end of the simulation, we can simply override the initial time at the final time instant of the previous simulation. And to the final time instant, we can set a very big number. Okay, the four-dimensional parameter space. It's just a quick look how can look like the collapse strengths in a 4D parameter space. Each subplot is a biparametric plot, and I just organize them in a 2D array. And that's how we can have a quick look at what can happen inside. Okay, I have a last example. I try to introduce it very quickly. It's a model of a pressure relief valve. It's including impact dynamics. The governing equations is a third order autonomous system. And the point is that x1 is the displacement of a valve, and at x0 it can hit the seat. So we have to specify an impact law also, which simply means that if the valve hits the seat, then we have to reverse the velocity of the seat. We have two parameters, flow rate, and we have restriction coefficients for the impact law. Okay, just quickly, we have to define even functions. The first one is just simply the Poincare section where the simulation have to be stopped. And the second one is for the detection of impact dynamics. X0 must be 0, is the detection of the hitting of the seat. And we have a specialized function called event action function, and it is called every time we have detected an event. And in this case, we can specify that what can happen in an event detection, and we can throw the trajectory to anywhere in the state space. What about the results? Here we can see a bifurcation diagram as a function of the flow rate. In the vertical axis, we have the maximum and the minimum component of the displacement of the valve. So if the minimum component, the blue curve, has 0, then we have impact dynamics. Okay, summarizing my results. So I already have a problem which is capable of handling many kinds of problems. But later on, we can extend it to make it more user-friendly, for instance, or include additional numerical schemes, or implement some efficient global or local couplings of identical systems. So thank you for your attention, and if you have any question, please ask.
So maybe I missed this in your talk, but when you solve ordinary differential equations, you usually use adaptive step size to speed up the calculations. Is there a way to incorporate adaptive step sizes into these types of calculations? Because you get a very strong skew in many cases.
Mm-hmm. As I said, I have two different algorithms. One is an adaptive step size, the Runge-Kutta-Kashkart method. It uses orders 4 and 5 to estimate the local error. So there is a possibility for adaptive step size.
How do you handle the skew then?
Sorry?
How do you handle the skew? Because if you start with two different parameter sets, then the step sizes will be different. So the runtime will be different.
You mean the warp divergence, or what do you mean exactly how I handle this skew?
We can discuss it later.
Okay.
Any other short questions? Maybe I have a short one. Can you generalize to multiple GPUs? Is there any difficulty?
I have never do that, but I don't think so. That's why I use this special class in which I can copy one portion of data in an object, and I can make multiple objects and assign different portion of data from the problem pool, and I can assign two different GPUs, I think. But I never do that because we have only single GPUs in the department.
Okay, let's thank Ferenc again.
Yeah, thank you.